So far, you have been taught what to do with electrons at fixed positions of atomic nuclei. Actually, this is only half of the problem, because nuclei are also to be considered, may be considered as quantum particles. And in many phenomena, the movement of nuclei is actually very, very important. So the question arises as to how one have to treat both electrons and nuclei as a quantum system together. Um, here we shall outline some ideas behind so-called adiabatic and non-adiabatic treatment of electrons and nuclei. So we start from the Hamiltonian of the whole system. So this consists of the electronic part, nuclear part, and electron-nuclear interaction. And the equation we need to solve is the stationary Schrödinger equation for the wave function psi, which depends on all nuclei coordinates, which are all behind this capital letter R, and all electronic coordinates, which are hidden behind this little letter X. And E would be the total energy of the system. And of course, you would expect that, as it happens in quantum mechanics, that this Schrödinger equation may have many solutions. You will get the ground state, the first excited state, and so on. So what are these Hamiltonians? So electronic Hamiltonian contains kinetic energy of electrons and the interaction of the electrons with themselves. Nuclear Hamiltonian also contains the kinetic energy of the nuclei. So here is the mass of the nuclei, which is about 1,000 times larger than the mass of the electron. And this is nuclear-nuclear interaction, just Coulomb interaction between nuclei. And finally, there is a term of electron-nuclear interaction, which is written here. This attraction between nuclei of charge Za and electron. And this is our full Hamiltonian. And in order to solve this very general problem of nuclei and electrons, we start from writing an equation, auxiliary equation, just for the electrons with fixed positions of the nuclei. So what we do here, this is the equation I'm talking about. So in this equation, I write the Hamiltonian of the electrons, kinetic energy, and the electron-electron interaction. I also write at here in the Hamiltonian electron-nuclear interaction and nuclear-nuclear interaction. So basically, I add here all the terms from our original Hamiltonian, apart from the kinetic energy of the nuclei. This is the only term which I left out. So this may be considered as electron-only Schrödinger equation, because nuclear coordinate R comes here as a parameter. It's fixed. And of course, we expect from the Schrödinger equation that there will be many solutions, all characterized by this index zeta. And the eigenvalues U, zeta, R would be some functions of the nuclear positions. So you will have that function for the ground state, electronic ground state, then another function for the first excited state, electronic excited state, second, and so on. So one can also say that this equation corresponds to classical nuclei, because we consider nuclei as fixed, not moving, so as classical objects. And that seems to be very intuitively correct, because nuclei are much heavier than electrons, more than 1,000 times heavier, because it's a mass of the proton or neutron is about 1,000 times of an electron. But you have many protons and neutrons in the nucleus. So nuclei are much heavier. So you would expect them to move very, very slowly. Electrons respond to this almost instantaneously. So you may consider, in fact, nuclear fixed and electrons just moving around for the fixed nuclei. But that would be there would be an approach in which nuclei are treated entirely classically. What we would like to understand is how to include quantum treatment of the nuclei in this kind of picture. So let's first consider an exact approach. It will also rely on that equation, because that equation still doesn't give us the full wave function. It is not just yet a solution of the Schrödinger equation. However, what that equation does give us is a complete set of these functions, electronic-only functions, which depend, however, on the nuclear positions as a parameter. Therefore, in order to solve the original Schrödinger equation, which is written both for nuclei and electrons, we can expand the total wave function psi into the basis of these solutions of electron-only equation. We are always allowed to do so. This is exact. And the coefficients of this expansion may still be functions of the nuclear positions. Why not? Because this function was obtained for fixed position of the nuclei. So what we need to do now is to take this trial wave function and substitute it into this Schrödinger equation, and then see what comes out of it. First of all, we need to understand that this Hamiltonian here is basically that Hamiltonian, electron-only Hamiltonian, plus the kinetic energy operator for the nucleus. So let's first act with this kinetic energy operator on this product of these two functions, which appear in the psi. If you perform this calculation, you will have to take account of the fact that not only the coefficients chi, these ones, depend on the nuclear positions, but only the electronic wave function parametrically depend on these positions r. Therefore, when we apply Laplacian to this product, we have to apply it to both terms. So that's why you have these three terms, because this is a second order operator. So if you perform this calculation, you substitute, you will get in the left hand side this this term, and you put the energy and the wave function into the left hand side as well. So this is what you get if you just substitute this trial wave function into the Schrödinger equation. So this is something you have to do yourselves. Just take a piece of paper and try to follow this mathematics. Then the first term is some of the terms are easy, because if you look here, for instance, this is the electron-only part of the Hamiltonian acting on the psi zeta electron-only wave function, and we know this is the u function times zeta, that u function here times psi zeta. So that term can be easily handled. So we obtain this equation here at the top of the slide, but it's still not yet an equation for the coefficients chi zeta. These are the coefficients we would like to obtain. So in order to have a closed set of equations for these coefficients, for these functions, what we need to do, we need to multiply this equation by the bra psi zeta prime, that psi, but with the index zeta prime, and integrate over electronic coordinates x. And this way we arrive at this equation here. All right? And that equation can be written down in a closed form here. This is actually not one equation, but a set of equations, because this index zeta prime we can run for all terms in this expansion here in this sum. And this set of equations would determine the total energy and the these functions chi zeta. Let's quickly have a look at these terms in that equation. And I urge you to actually derive this. Sit down and follow the explanations I have given to you and derive these equations yourself, taking a piece of paper and a pen. So first of all, this operator. This operator contains a diagonal element with a kinetic energy operator for the nuclei. And it contains this another operator, which is called non-adiabatisti. It is a matrix operator, so this term is diagonal. However, this is not. It contains also apart from the diagonal elements, also off-diagonal elements. But that term can be written as the sum of two terms. The first term, so we sum over all nuclei here. Capital A corresponds to nuclei and alpha to x, y, z. So we sum over all nuclei. This term is just the matrix element of the electronic wave functions with the kinetic energy operator of the nuclei. Remember, this psi, zeta, they do depend on the nuclear coordinates as parameters. So we have this term here. And we also have another term in which this d is a similar operator, but with the first derivative with respect to the nuclei. But it also has this operator, the differentiation with respect to the nuclei coordinates. So that term is actually an operator, but the first order differentiation. This kinetic energy is the second order differentiation. And there's also a function, not an operator. And finally, this term here is just a diagonal matrix of eigenvalues of the electron-only equation. So these u's in the electron-only equation appear here for zeta equals zeta prime. Interestingly, this d term for zeta equals zeta prime is actually 0. This is because if you consider zeta equals zeta prime, for that diagonal element, you arrive at that matrix element, and that matrix element can actually be written as a 1/2 differentiation of the normalization of the wave function. And therefore, it is 0. If it was a non-diagonal, you can't do this because you apply here this differentiation operator only on the right function, but not on the left function. So this trick can only be performed on the diagonal elements. But for the diagonal elements, therefore, these d's are equal to 0 exactly, and therefore you don't have this differential operator. So differential operator here appears only for off-diagonal elements of the non-adiabaticity operator. Okay, so this was a very general, very formal theory. So we were able to write the wave function of the whole system, electrons and nuclei, as a linear combination of electronic-only wave functions for different states, the ground state, first excited state, maybe second excited state, with the coefficients which are themselves depend on the nuclear positions. And we managed to write a system of equations for these coefficients, which are themselves functions of the nuclear positions, in a closed form like this. And this is rather complicated matrix set of equations with of the second order differential operators.